recording. Go. Yeah, that was the last thing. Yes, we should go to today's lecture. And we continue with well, some nutrients. Nitrogen is an old thing. It's early 1900 when one learned to realize that how to synthesize ammonia from air, and it's nitrogen gas plus hydrogen gas goes to ammonia. This is actually a spontaneous reaction, but it is a large activation energy barrier. But as soon as that could be solved, then one can use the ammonia partly converted to nitric acid and then combine those two in order to form ammonium nitrate, solid powder that you can sell as fertilizer. That means that nitrogen fertilizers, they are available essentially in unlimited amounts. It only costs some energy to synthesize ammonium nitrate, and ammonium nitrate are easily absorbed by very many crops, and the nitrogen in them is used. On the other hand, not only nitrogen is necessary, potassium seems to be necessary because I think sodium is much more common, but which is also necessary metal or a necessary nutrition element. But sodium is, there is no lack of sodium, I think, but perhaps a slight lack of potassium. So that is normally added to fertilizers. There are quite small amounts necessary, and well, they don't come from any sustainable source, so to say. They come from, you need to dig them out from mineral deposits in the ground. But I'm not sure what the problem it is. You can extract it from seawater, and in that respect, there is also a very, very large reservoir, and perhaps in practice unlimited. When I say unlimited, I don't mean that the source is very large, but actually more or less infinite, because it is recycled. Nitrogen is recycled, and the end product of nitrogen cycles are usually nitrogen gas, so return to the atmosphere. And as long as we're not using a lot of the nitrogen in the atmosphere, so nothing will happen with the atmosphere, hopefully. And the same, I think, applies to potassium. If one would extract it from seawater, then eventually the end, final end of potassium would also be drainage from land, and the water would flow out in the sea. Phosphorus is perhaps the most serious source problem, actually, that we have. Resource problem for fertilizers. Phosphorus and nitrogen, they are necessary, but phosphorus is mostly it comes from mineral deposits, and also I'm not very updated, but something like 80 to 90% of the phosphorus sources in the world come from West Africa. And for the moment, it is perhaps stable source, but I mean, the problem is that it is a limited source. I'm not sure. Do we suffer phosphorus limit something like 50 years in future, or 100 years in future, or something like that? But it is at least those time intervals that is realistic. The price of phosphorus will increase quite much when all of these cheap resources are used up. Phosphorus is available from a lot of places. For example, from sludge from the ocean floor and sludge from wastewater cleaning plants, but it needs to be taken care of properly. And we don't want to pour out fertilizers containing some metal ions that we don't want, for example, cadmium and mercury. They should be abandoned in every possible case. Cadmium is occurring naturally at low levels in phosphor deposits and phosphor-bearing minerals. But if it's enough low, then one can perhaps accept it. If you look at the cadmium content in Swedish cereals, for example, like normal crops that we bake bread of and such things, there is maybe 1 ppm or something like that cadmium instead of calcium in the phosphates. I don't know. The Swedish Livsmedelsverket, the food administration agency, they do have some limit values, I'm sure. But and I think also that most of the cereals that one can buy here is well below those limits. But it's not zero. The level is far from zero. You can measure the level of cadmium in very many foodstuffs. This is not a, I mean, this calcium or cadmium, there need to be some counter ions to phosphor or to phosphates. Most of the phosphorus is occurring as phosphate. But and calcium phosphate is very, very common. But of course, you need to check the presence of some other metals. Calcium and cadmium are very similar in size and in charge. They're slightly dissimilar when it comes to acid-base properties. And that non-similarity is enough, I think, for cadmium to play a completely different role when it comes into living tissues. For example, it binds very heavily to sulfur. And I said previous that sulfur binds to transition metals in proteins, but this is a transition metal, so it binds very heavily to sulfur. So what's the point? Well, there is also, except transition metals, there are other sulfur-containing proteins in living tissues. And so fixing a cadmium ion to those sulfurs will perhaps disturb the properties of those proteins and perhaps be dangerous and lethal. One should, not all the nutrients are absorbed in crops. especially those that are water soluble, they dissolve in rainwater and drain out in lakes and sea. This is a possible problem with, for example, the Lake Baltic and the algae blooming, that perhaps too much nutrients are coming from drainage of land. So in principle, wastewater should be purified from both from nitrogen and phosphorus. It's very easy to purify wastewater from phosphorus, but it's less easy to purify it from nitrogen. We will come to that. There is a quote sometimes named Redfield code between nitrogen and phosphorus, that is something like 16 or possibly 7, depending on what unit you have. If you have a molar unit or weight unit, there are different values of this. Since phosphorus is heavier, it's a larger molar weight than nitrogen, there will be different values. But you can see that nitrogen is the dominant. Approximately 10 times more nitrogen than phosphorus is necessary for optimal growth. I think this comes from analysis of the composition of living things. If you take a vegetable or a small mouse or something like that and determine the nitrogen or phosphorus content in those creatures, then you will get approximately something like that. So the nutrients should also be to farms should also be supplied in the same amount. So the easily accessible nitrogen and the less easy accessible phosphorus in more nitrogen than phosphorus, and a minor amount of potassium and perhaps other elements also. Removal of nutrients in wastewater is of interest, at least in order to delimit the eutrophication, that the sea and the lakes, the recipients essentially, that they grow full of vegetation. It's not poisonous, except when the vegetation dies and fall down to the bottom of the sea, then it may produce some, then it may consume the oxygen and produce some poisonous environments due to hydrogen sulfide. But otherwise, eutrophication, it's perhaps mostly a it's mostly about the aesthetical point of view. But we want fresh water from lake water without any algae, or then it would be much more difficult to clean it. Wastewater treatment, you can find on the internet a lot of information about, for example, the Stockholm Vatten. I think it is the same, or if you Google for Stockholm wastewater or something like that, you will easily find a lot of information. I will also put up on Athena soon a few brochures and some texts from Stockholm Vatten, from both freshwater plants and wastewater plants. If we look at different contaminants, for example, nitrate is a common fertilizer. Where do we find contamination of too much nitrate? Well, in US, this map comes from high nitrogen input, and is the high vulnerability of the is it a high risk that it will flow out in lakes and rivers? Yes, of course, when we use a lot of nitrogen. This is clearly areas with a lot of agriculture, with a lot of farmers. I've never been in California, but in this part I seen a lot of large fields in US, but I suppose that's the same situation here. So, and the reason why do we have nitrate contamination of nature is probably as easy as farmers add enough fertilizers and then maybe a spoon extra just to make sure that the crops get enough. The nitrate is not very poisonous, but not directly at least, but it may give rise to other side effects like eutrophication and perhaps poisonous lake bottoms and such things. Yeah, we've seen these before. We should try to analyze nitrogen in the lab, perhaps. Ammonium and nitrate, they are not very high levels. So this is a difficulty actually, because of the low levels. It's very problematic with self-contamination. It's enough that you stand at a lab bench and breathe, and what kind of nitrogen containing compounds do you breathe out? Maybe ammonia, maybe uric, urea and uric compounds, maybe some other nitrogen containing compounds, and these are enough to actually produce at the levels that we are interested in to contaminate the sample. So we would have needed a clean lab, and we don't have that, so we will forget about trying to analyze nitrogen. There are easily available methods. For example, nitrate plus resorcinol make a reddish pink complex, or ammonium and some other compounds make a blue complex. So then just mixing in these reagents, checking how reddish pink will the solution be, or how bluish will it be, then that's an easy way to analyze nitrate and ammonium. But as I said, you need to take care in order not to contaminate. Perhaps one should have an automatic machine for this type of analysis. There are also ion selective electrodes, and those we actually have, so we could try them if you like. But unfortunately, the electrochemical methods, they are very easily applicable, but usually the levels that we have in real lakes and rivers and such things, they're too low levels for these electrodes to react reasonable. If they do react, then it's enormous levels, or not enormous maybe, but way larger than usual. So these spectrophotometric methods, they are more sensitive. But both of the electrode detection is very convenient, and I think that very many wastewater plants, they measure both from a traditional wet chemical point of view, but more or less all the time with electronic equipment, because then they can log, for example, how the levels of ammonium or nitrate, how it varies with time and such. Yeah, this is the same as we looked at previous. Nitrate and ammonium is of interest, but you need to. It's not the same. Yeah, no, it's not the same. But you need to do an analytical calculation if you should, for example, in point A here, determine how much ammonium is it, or in point B, how much nitrate is it. It's quite far away from nitrate area in point B, so you could easily draw the conclusion that it should be quite much less than ammonium, and essentially close to zero far away. If you would be very, very close, for example, very, very close to what? To the, if you would be here on the line, what is the composition between, is it mostly nitrate? Or is it ammonium? Yeah. Any suggestion?
I would guess it's 50-50.
50-50. Exactly. Correct. And then if we go slightly inside here, what would you guess then? This is considerably more difficult. You can give an approximate answer.
If it's inside,
The nitrate area?
like the percentage.
Yeah. What do you think?
90%.
Yeah. And of nitrate, yes. And 10% of ammonia. This is important, the thing that you do now. You do an estimate, but one shouldn't be.
Can I ask a question?
Yes.
I do understand why it's NO3, but I don't understand how you got the percentage right.
He was guessing, I think.
So it's just a guess. We
Yes.
don't know the percentage.
No.
Okay.
I have problems with my computer. So try again. Yeah, but it. I mean, hey, sorry. So, you can't be say up here. You are inside the nitrate area, so the quote of nitrate to ammonium should be bigger than 1, or maybe much bigger. 90% divided by 10% is bigger than 1. Or I would say that you have a majority of nitrogen. Let's see this point A here. I think we have measurement values. for that at pH 6, and I'm not sure. We'll see what's available on the next pages. If we want to do so, you need to find the actual formula for the equilibrium between the upper part and the lower part. Or I mean, it's not doesn't matter if you have the opposite, but preferably give everything as reductions, because I think the constants, for example, the PE naught or the E naught, are available for reductions. So in this very case, the PE was 11 and the PE naught is 14.15. Does it fit with the figure? 11, yeah, maybe 8, and then 10 is in between, and 11. This is perhaps more or less accurate. 14.15, what is that? The PE naught, that is the PE at pH 0. 14.15, yeah, why not? And then we have a line that is sloping. A problem is perhaps that it diverges into an area of NO2 minus here, but we can think away the NO2 and think about this line as continuing as the border between the ammonium and the nitrate ions. And then using this PE formula, there is no 1 upon n here in front of it. So then we did use the bottom version here, the bottom equilibrium formula. This is the right-hand side, ammonium raised to the power of 1/8 and water to 3/8. Ammonium to 1/8 and water to 3/8, yes. And nitrate and hydrogen ions. And one of these things could immediately be removed because the water is probably unit activity. It's a dilute solution. So then, and the H plus here could be factored out. This is a little bit like an exercise in logarithmic laws or something like that, but I think this is correct. It is plus 10 divided by 8 times the logarithm of H plus. This is in the denominator, but it is a negative sign here. So then I think this should be plus here. Noting that plus logarithm is the opposite of minus p. We can sort of simplify if it is a simplification, I'm not sure. And then calculate this quotient of ammonium ions to nitrate as the logarithm of that is minus 35 nearly, which means that where is it? It's ammonium ions is 10 to the minus 35 times nitrate. What does it mean? It's 35 orders of magnitude more nitrate than ammonium. This is horrendously large number or small number, maybe. I call both small numbers and large numbers for large numbers sometimes. That is a problem. Maybe. They are far away from unit. What does it mean? Go back to the diagram. And the point A here is dominated by nitrate that you saw previously. And Kevin would have guessed that it is 99% or 99.9% of nitrate. But from the, wouldn't you, Kevin? a lot nitrate. But here you see that the quote of this one is enormously away from zero. So it's essentially only nitrate. But there is a small possibility. I mean, this is perhaps of academic interest, not in reality. We could say that it's only nitrate because it's less than a nitrate ion in, what is it, a billion moles or something like that. And that is not of interest, not from a real reality perspective. We can do a few of these. I mean, the problems with this is essentially handling of the logarithmic reaction quotient here. And perhaps sometimes to simplify. Is it the simplification that we have done this? Yeah, maybe not. We could also, with modern day calculators, instead of say factoring out this pH here, just put in the hydrogen ion concentration, the value of it, and use it in an expression. And then suppose you would have get plus 34 here. That means ammonium ions is much more frequently occurring than nitrate. Does it fit with the diagram? Why should it be more ammonium ion in point A than in point B? It should be than nitrate. And then you could be sure that somewhere there is a plus or minus sign error. This is not so serious. It is serious maybe if you base political decisions that you do some calculations and you draw some conclusions that is opposite to reality. That is not so good. But if you're several people working in a political environment, then and if you do produce the same results, then you couldn't trust them, I hope. So since we're not able to analyze nitrogen very easily, what we will do in the lab, we will in lab 2 actually, we will take some samples and check for the other fertilizer, phosphate. That is quite easy to and much less susceptible for contamination, because you don't breathe phosphor containing species, I hope, unless you have some serious disease. We can make a colored complex from the sample via some reagents, and then we should reduce them also to get to see the blue color, and then it's just simple spectrophotometry with a standard curve or something like that. Now let's see, how much time do I have? 10:44. Maybe we should stop here actually, and then we continue with cleaning of water and such things tomorrow. Is that okay?
Yes.
Yeah. So this afternoon we have some calculation exercises. I think there are some parts now that can be looked upon in exercise 2, containing Porbet diagrams. And you could also have a glimpse at exercise 3. They are, yeah.
Sorry. Are you done?
Yeah.
Can you explain a little bit about the lab we're going to do? Because it's going to be different, right? It's not going to be like in the lab having a normal experiments.
Yeah, well, I stopped there. Should I stop there?